Hi everybody, I'm going to present you PowSyBl library. I'm Anne, I'm community manager and the developer of that project. I'm working for RT, the French TSO. We use PowSyBl to model our power grid. PowSyBl is an open source set of power system blocks, written mainly in Java, dedicated to grid analysis and simulation. PowSyBl is a project of the Linux Foundation Energy since 2 years. It is licensed under Mozilla Public License version 2.0. We are hosted on GitHub at www.github.com/PowSyBl. The community involves 77 people, and PowSyBl is production ready. It offers a set of features for grid modeling and simulation. For example, you can use PowSyBl to create a state-of-art application able to handle a variety of formats, such as CGMES for European Data Exchange, to perform power flow simulations and security analysis on the network, or to display single line diagram of the substation you can have in your network. All the features for grid modeling and simulations are fully described in our website. Here you have a full description of the grid modeling and a full description of how you can extend the grid modeling for your specific needs. You can find here all the grid exchange formats that we support. So, for example, we support also PSSC formats, IEEE, Mad Power. You can perform a lot of simulations with PowSyBl, like power flow, security analysis, or time domain simulation. For that part, we rely on an open source project called Dynamo. PowSyBl offers some advanced features like high performance computing or data management, as time series management or database management. We also provide a set of microservices around the blocks. You can have also with PowSyBl a Python binding to make some proof of concept around PowSyBl. A key feature of PowSyBl is its modular design at the core of the open source approach. It enables developers to extend or customize its feature by providing their own plugins. You can see here our roadmap. It is what we expect to do next year. And here you have the community. The community exchange on Spectrum for questions and issues. And you have here our Slack for more daily conversation. If you want to participate to our public technical steering committee, please have a look at our LFE calendar to join. PowSyBl is already used in a number of projects. You have Pharaoh. Pharaoh is an open source modular toolbox for power system coordination process. Dynamo is an open source time domain simulation tool for power systems using the Modelica language. And GridSuite is a suite of web based tools for grid simulation analysis. And my colleague Yon is going to present that tool to you.
Hello everyone, I'm John, a developer from the GridSuite project. GridSuite is an open source project developed at github.com/GridSuite. Please come and check it out. The goal of the project is to build upon the PowSyBl project and offer easy to use tools used to perform many different tasks that are needed to run coordinated electricity grids, such as the European electricity grid that we're seeing right now on the screen. Today, I'll be giving you a brief tour of our first tools, and we'll talk a bit about how we make them. Let's start with the Grid Study tool, currently on screen, which is displaying a beautiful map of the European grid. It's got colors to differentiate between the different voltages, and you can zoom and pan and even get this stunning European view. Okay, let's switch to the French network now. We see here a list of available networks in different formats, for example CGMES or UCT. Right now we're displaying the map with a dark theme and straight lines between the substations. Let's switch it over to a lighter theme and to lines drawn by the GPS positions of all pylons in the line. And now we have the whole view of the French network with accurate GPS positions for all the lines. We can even get a feeling of how the power is flowing through the network when zooming in and seeing the little arrows that are animated along the lines. To get this smooth map with 60 FPS animated arrows, we use the awesome library called DeckGL, which uses WebGL under the hood to get the performance. On this map, we can simplify things to get a better overview by displaying only the higher voltage levels and by hence showing the French backbone, electricity backbone. On the left side, we get a list of the substations in the network, in which we can search for one substation using this filter, which is really fast. And we can ask for substation single line diagrams, where you see the different voltage levels of the substation, or for only one voltage level. Grid Study is a tool to explore networks, so we allow interacting with these single line diagrams, for example by clicking on these breakers, which will toggle them. It will open closed breakers and close open breakers. The GridSuite is also a collaborative tool, so we allow sharing links to our work to work with colleagues. Let me open this link in another browser to simulate another colleague working with me on this case. The link brings him directly to the same substation as the one I was looking at. Notice two things about this single line diagram. It's got only one voltage inside this whole voltage level, which has a computed value of 243 kilovolts. And it's got, on this line, 77 megawatts of power going out. As a first demo, I'm going to click on this breaker. I will open this breaker and disconnect the two bars from one another. This should trigger the topology recomputation on the fly, and it should be visible immediately live in my window, in my browser window where I click on the breaker, as well as in the other browser where my colleague Bob is just watching. Here we go. The app now shows us that we have two voltages, one with the light green and one with the dark green, but their values are unknown yet. This is because the app has only recomputed the topology, but not all the electrical values. To recompute all the electrical values, we need to run an electrical simulation. The simplest kind of electrical simulation is called a load flow simulation, and it computes the steady state of the voltage and power throughout the grid based on the constraint of the power plant's production targets and the consumer's demand. Let me also open this breaker here, which should, after we recomputed the values, show that the power is no longer 77 megawatts flowing through this line, but instead it should be 0 because the line has become disconnected. Let's run the load flow. The load flow is of course delegated to PowSyBl, and here we see the logs of the computation. And now we see the updated value of 0. To run this load flow, we use the PowSyBl framework, and we ship the code from PowSyBl in Docker containers that we deploy either in a Kubernetes cluster, which is what we use to run our public demo at demo.powsyble.org, or for simpler deployments like the one I have now, using Docker Compose. This is what we're seeing with these logs. To get live feedbacks on all operations, we use an asynchronous architecture and send messages through brokers like RabbitMQ and through WebSockets back to the browser. For the servers, we chose a stateless approach because it gives us a lot of power to easily develop new features. It is such a powerful model because any computation can fail and be picked off by another process where it left off. All computations are stored in a database as soon as they're done. We're using a scalable database as well. We use Cassandra, so we're confident that our platform can be used by many users at the same time. Deploying a new version is easy as well because there's no state in our code, so we can just replace the previous version with the new one. Everything is persisted in the database. And that's how our continuous integration and deployment works, by taking merges to the master branch on GitHub and triggering GitHub actions that end up recreating pods in the Kubernetes cluster. Okay, back to the app. In addition to the geographical map, we can see a table of all the elements in the network, and this table can even allow you to interact with the elements, for example, by setting new targets for productions and rerunning simulations. We can also see the results from the simulations. Load flow simulations are not the only simulations that you can run. Another type of simulation is the security analysis. Running a security analysis means checking one by one for a list of predefined contingencies, whether or not they affect the network. For example, in this case, I could ask for the platform to run a simulation for in case each of the lines of the 400 kilovolt lines in the network had a problem. So this would mean running for this network 867 contingencies and getting results on which lines, when they have a problem, cause disruptions in the network. We're not going to do it because for this you need more than the simple Docker Compose deployments, or else it will take a very long time. Speaking of predefined contingency lists, we made a very simple app that allows you to create them. It's very simple because it's based on the PowSyBl contingency domain specific language. We use React, the front-end JavaScript framework, to make these apps, and it's really fast to build. Here we see the contingency that I used earlier. It's only a few lines of code because PowSyBl makes it very easy to write those contingencies. A real groovy script that uses the PowSyBl contingency DSL, domain specific language. One last task that is useful in coordinated networks is to get network data from the different grid operators that are connected together and verify that their individual grid models are coherent and can be merged together in a merged grid model, and that this model is also stable using a load flow simulation. So we have this tool called Grid Merge, which will run these kind of workflows as soon as grid operators publish their data. Let's simulate the publishing of the data by grid operators and see what happens in the app. Here, this script will simulate the publishing of the data. So we see here that the app received a network and is running a load flow on it, so it's light blue until a load flow determined that it's correct. Now it's gotten dark blue because the load flow on this network said it was okay. The same happened for the next network, and now the networks have been merged together and the load flow has been run, and green means okay. We see the process being repeated every hour as our script is simulating the data sent by grid operators. Receiving, computing, receiving the second one in an instant, receiving the second one, computing the load flow on the second one, and then computing the load flow on the merged network. Okay, that's it for the demo today. In the future, we plan to make more tools that cover more of the tasks needed to run an electrical grid and improve the current tools as well. For example, we want to be able to quickly describe variants of networks that would be the same as opening a switch or opening a breaker or closing a breaker, but instead express the fact that we want to maybe add a substation or add a line between two substations, or maybe change the demand for power. We also want to add simpler ways to describe simple contingency lists, where you don't have to resort to writing even a short and easy script. We would like to get a GUI that will help you, sort of a wizard that will help you creating contingency lists. For the grid merge tool, maybe getting more alerting and more results would be a nice feature. So maybe sending emails as soon as one individual grid models fails the checks or something like that. These are just a few of the improvements that we're going to make. Please check out github.com/gridsuite regularly to see what we're up to. Thank you for watching. Bye.